Have you ever gotten that feeling that there's some kind of hidden language that describes everything around us? You know, a secret code that connects things that seem totally, completely unrelated? Well, you're not wrong. It turns out there is. And today, we're going to decode it together.
Okay, picture this, an invisible river of air flowing over a race car at top speed. It's a problem of fluid dynamics, and engineers have to figure out exactly how that fluid moves to stick the car to the track and slash through the air.
Or how about the sound coming from a guitar? When you pluck a string, a wave literally travels down its length, right? It creates these vibrations in the air that our ears pick up, and boom, we hear music. Now let's think even bigger. How on earth do we predict something as massive and, well, chaotic as the weather? We're talking about modeling these enormous systems of heat and pressure that are swirling all across the globe.
So you've got airflow, you've got sound waves, and you've got global weather patterns. I mean, they seem like they're from different worlds, right? So what is it? What's the common thread, the fundamental rulebook that governs all of them?
Well, the answer is a branch of math called partial differential equations, or as we'll call them, PDEs. And this is the cool part. You could say they are quite literally the language the universe is written in. They are the mathematics of how things change, move, and evolve. Okay, so what exactly are these super powerful equations? Let's break it down and get a really clear definition. So let's imagine a simple metal rod. We'll call its temperature U. Now, at any given moment, the temperature isn't the same all the way along the rod, right? It changes depending on where you are, that's its position, x, and it changes from 1 second to the next, that's time, t. A PDE is simply an equation that nails down that exact relationship. It's a way to describe how something changes when it depends on more than one thing at once. Now, here's what's so fascinating about all this. It turns out that most of the physical stuff we see happening around us can be boiled down to just 3 fundamental types of PDEs. A better way to think about them is as the 3 essential stories that nature loves to tell. Our very first story is all about things that travel. This is the story of propagation, and the equation that tells it is, you guessed it, the wave equation. Let's go back to that guitar string. When you pluck it, you create a wave, and that wave is basically a piece of information that travels from one end to the other and back again at a very specific speed. And, this is key, it doesn't just fizzle out. Light waves, sound waves, even the ripples in a pond, they all follow this exact same story. In this equation, it might look a little intimidating, but it perfectly captures the physics. It's actually just Newton's famous law, F equals ma, but rewritten for one tiny little piece of that vibrating string. All it's saying is that the acceleration of that piece is tied to its curvature, how much it's bent. It's so simple, but incredibly powerful and honestly, really elegant. So that's our first story, information that travels. Our second story is about something completely different. It's about how things spread out. This is the story of diffusion, and it's described by the heat equation. Just imagine dropping a little bit of ink into a glass of water, or feeling the heat from a flame spread from one end of a metal spoon to the other. That whole process is diffusion. And unlike a wave, it's a one-way street. It's irreversible. You can't just unmix that ink. Over time, all the sharp details just get smoothed out as everything moves toward an average. So what's going on here? Well, this equation comes from a really basic fundamental principle, the conservation of energy. It's just a mathematical way of saying that heat doesn't just disappear into thin air. It has to go somewhere. It flows from hotter areas to colder areas. That's it. And that brings us to our third and final story. Now, this one isn't about change over time. It's about the end of the line, the final state of balance. And this is governed by something called Laplace's equation. So, after that ink has completely mixed into the water, or after that metal rod has cooled down and reached a totally stable temperature, what do you have left? You have equilibrium. Everything is in balance. Laplace's equation describes this final steady state, where the system is done evolving. It's basically the end of the story for all those diffusion problems. And the intuition here is just beautiful. This equation is basically saying that when a system is in balance, the value at any given point, whether that's temperature or pressure or whatever, is simply the average of all the values immediately surrounding it. Everything has been perfectly smoothed out. And here's a cool little connection for you. Ever wonder why this type of equation is called elliptic? Well, it's because the mathematical form that's used to classify it just so happens to be the same as the algebraic equation for an ellipse.
So this really abstract math concept is directly tied to a geometric shape we all recognize. Pretty neat, right? So, okay, we've got these three fundamental stories that describe pretty much all of physics. But how do we actually use them to design a race car or predict the weather? Well, that's where we turn them into reality using computer simulations. Let's take something called computational fluid dynamics, or CFD. It's a really amazing process that happens in three main stages. First, you've got the preprocessor. This is where engineers build a digital model of, say, that race car, and then they break its surface into a grid of thousands or even millions of tiny cells. We call that a mesh. Second, the solver gets to work. This is the real number crunching part, where the computer just painstakingly solves our PDEs in every single one of those cells. And finally, you get to the post-processor, which takes that absolute mountain of data and turns it into these beautiful, colorful visuals that we can actually look at and understand. And why go through all that trouble? Because it is incredibly powerful. CFD lets engineers test out new designs way faster and cheaper than building physical prototypes. It lets us study things that are too big, too dangerous, or maybe even impossible to test in the real world. And the level of detail you can get is just unbelievable. Okay, let's bring this all home. Understanding these equations, understanding these stories of propagation, diffusion, and equilibrium, it's like learning the fundamental grammar of nature itself. It really gives us a deep insight into how the world actually works. And that insight, that's the whole point. You know, the computer pioneer C. Hastings said it perfectly way back in 1955. The purpose of computing is insight, not numbers. Solving these incredible equations isn't just about getting a huge dump of data. It's about gaining a much deeper understanding of how a system really behaves. So you now know the three basic stories the universe tells through the language of physics. The only question left is, as you look at the world around you, from the steam rising out of your coffee to the ripples in a puddle after it rains, what will you see differently?